Cannot find my slide. Wait, give me a minute. Okay.
Yeah, I can see. Okay,
Oh,
so let me introduce you first, then you can start. Okay, Dr. Yu Shuhen, he graduated from NUS here for his bachelor's degree in the material science and engineering, and is currently a research fellow in chemical and biomolecular engineering in National University of Singapore. He received his PhD degree in 2019. During his PhD study, his experience in synthesis and characterization of earth-abundant catalysts for electrocatalytic hydrogen evolution reaction. In particular, he tailored the physics and chemistries of various transition metal sulfides and transition metal phosphide materials, such as vanadium sulfide, moly sulfide, cobalt phosphate, and nickel phosphide for improved HER performance synergistically. Currently, he's working on nanostructured copper-based catalysts for electrochemical reduction of carbon dioxide. Okay, so without further ado, I would like to invite Dr. Yu to start this presentation.
Hi, thank you, Prof. Lam. Hi, good evening, everyone. My name is Shu Heng. So today I would like to share with you what I did during my PhD work. So basically, what I did for my PhD work is to fabricate hybridized electrocatalysts for water splitting. In particular, I focus on hydrogen evolution reaction. So future energy, the criteria for future energy, it has to be green, sustainable, and renewable. Green means it does not generate greenhouse gases, for example, like methane, carbon dioxide. Sustainable means it will not be depleting very soon. For example, like fossil fuel is going to be depleting very soon, so it's not sustainable. And renewable, fossil fuel is not renewable because it takes very long time to recover from the biochemical process. So what are the future energy resources that satisfy green, sustainable, and renewable? There are, for example, green energy, solar energy, and wind energy. So after we harvest this energy, we need to store them, for example, in the form of lithium-ion battery. This is in the form of electrochemical energy, or we can store the energy in the hydrogen and oxygen by water splitting. So this is in a form of chemical energy. So hydrogen is proposed as a fuel for future due to its abundancy and high calorific values. If you don't want to burn it, you can convert hydrogen into electricity with the oxygen and with the water as a byproduct. Last but not least, we can also see that the hydrogen has a low viscosity, meaning to say that it is readily to be transported in the pipeline, in household, or in the industry. So traditionally, hydrogen is generated through steam methane reformation and coal gasification. So these two processes must happen at high temperature, for example, like 1000 degrees C. Now, in generating the hydrogen, for every 4 hydrogen generated, there will be 1 carbon dioxide generated. And for coal gasification, this is also the same. For every 2 hydrogen generated, 1 carbon dioxide will be generated. So this process is not very green. We can actually split water by heating the water very high temperature. For example, like 2000 degrees C. This is called thermal water splitting. However, it's not economical. Or we can perform water splitting at a lower temperature, but with the assistance of catalyst. This is called thermal chemical water splitting. Of course, it's also not very economical. So water electrolysis is a very promising method because we can split the water electrochemically at room temperature for about 1.23 volts and above. So basically, we can apply a positive potential and a negative potential across a shell. It will generate oxygen and hydrogen. So the advantage of water electrolysis is that we can generate high purity hydrogen and oxygen. There's minimal pollution because there's no carbon dioxide generated as a byproduct, and is readily to be converted into electricity with the fuel cell. So this is the water splitting design called electrolyzer. So if you apply potential above 1.23 volts, then you can generate hydrogen at the cathode and oxygen at the anode. So currently the state-of-art electrocatalyst to generate hydrogen is platinum for cathode and iridium oxide and ruthenium oxide for anode. So if you like to, if you can also insert a membrane here so that the hydrogen gas and oxygen gas cannot like cross over, and you can get high purity oxygen and high purity of hydrogen and oxygen. However, there are some issues for the platinum and the iridium oxide. They are very scarce. They are not very prevalent, and also because of this reason, the cost is very high. So water electrolyzer usually do not apply platinum and iridium oxide, although they are the state-of-art catalyst, because the cost is very high. So for this reason, my project focus on developing high activity earth abundant catalysts. I'm trying to find some low cost method and some earth abundant element. So what happened in this electrolyzer? We have hydrogen evolution reaction. In cathode, we have proton begin reduce, and anode we have water begin oxidize. So this is the overall total water splitting reaction. All right, so I'm going to talk about the mechanism of hydrogen evolution reaction. So this is a scheme of the hydrogen evolution reaction. So in the first step, we have absorption, and the second step, the activation process, where the hydrogen density will start to deviate. And then we have a diffusion of the intermediate. For example, two adsorbed hydrogen can combine to each other, they diffuse and combine to each other. Or we can have the proton approach the adsorbed hydrogen because the proton is more mobile. And then with the assistance of electron, then the proton can reduce and it will form a molecular hydrogen. So transformation of chemical bonds and desorption of the molecular hydrogen. So this is a general scheme of the HER reactions. So if you can change any of these steps, you can manipulate the mechanism or the speed of the HER reaction. And then we have very famous volcano plot. So basically, we need to find a catalyst that have a moderate interaction with the catalyst surface. So if we have a very strong interaction of the catalyst with the hydrogen, then the absorption process is favorable. However, the desorption process will be unfavorable. So the overall reaction will be sluggish because the desorption process will be the rate limiting step. On the other hand, we can have a weak catalyst and hydrogen bond interaction. So because of the weak interaction, the absorption step is rather slow. However, the desorption step of the molecular hydrogen is fast. Overall, the reaction will be slowed down as well. So we need to find a catalyst that have optimal interaction rather than strong interaction. So that would be the platinum, which can be visualized by the volcano plot. All right, so now I'm going to talk about the earth abundant electrocatalysts. For example, transition metal dichlorogenide, transition metal phosphide, transition metal carbide, and so on. So in my project, I try to fabricate transition metal dichlorogenide, including MOS2, WS2, BS2, nickel phosphide, and cobalt phosphide. So currently, the challenges of the earth abundant electrocatalysts is that they have very limited of the active size. So in the slide, we see the MOS2, the H are the active site and the basal plan are not the active size. So we need to do something to increase the active size. And it has low intrinsic catalytic activity. We can do chemical doping. We can do a lot of things to increase the intrinsic catalytic activities. It has poor electrical conductivity. Although some of the material here are termed as a conductive material, but they are only relative to the semiconductor. They are not referred to the metals. So we can need to do something to improve the electrical conductivity of this material. Yes, unsatisfactory long-term stability. Some of these materials are very active. However, the stability will be compensated. So these are the challenges that we need to tackle and to develop a very good high performance electrocatalyst. So these are the strategy of designs for catalysts. Basically, we can play with the intrinsic activity, or we can play with increasing the number of active sites. So how do we increase the intrinsic activity? So these are the results reported in the literature. There are something called intercalation. For example, you can intercalate lithium ion into the MOS2 structures. As you increase the amount of the lithium ion, then the 2H structures of MOS2 will start to become 1T prime MOS2 and so on, because the material, the layer can slice over each other as we increase the lithium amount. Also, we have something called alloying. So if you put more chemical in the material, it's called alloying. If the material is not enough, then we say it's doping. You can have core shell structures. We have adsorbate-adsorbent interaction, quantum confinement, polymorph, and so on. These are the methods used to control the intrinsic activity, to improve the intrinsic activity of the material. On the other hand, we can also increase the number of active sites. If we increase the number of active sites, what we can do is nanostructuring. We make the material smaller and smaller, or we can use conductive electrical supporter, for example, like carbon nanotube, so that the catalyst can be well dispersed on the supporter. Or we can do some shape controlling to expose more active sites to the electrolyte. Certain shapes, certain crystal will have more active sites, so that it can be exploited for HER reaction. So the problem here is that we cannot always increase the number of active sites as we want, because as we do nanostructuring, theoretically, we increase the number of active sites, but at the same time, the stability of the material will be compensated. So for bulk material, the structure is well crystalline. However, when you nanostructure the material, it becomes more and more amorphous. So the stability will be compensated. So most of the HER scientists, they will try to do the two things together, increasing the intrinsic activity as well as to increase the number of active sites at the same time, while trying to keep the stability at the practicals for practical application. So this is the objective of my work during my PhD. So to enhance the performance of electrode via hybridizing electrocatalyst, to develop a transferable hybridizing approach. Transferable means I can apply this method in this system and also another catalyst system. So this method is more like a universal method. To simplify the hybridizing process, maybe one step or two steps at most, to engineer electrocatalysts with high current density, because many catalysts, they are very active, but they are meant to be tested at low current density. At high current density, maybe they suffer from a stability issues, or the sample could detach from a supporter. So I need to find a way to make a very robust or durable catalyst. As such, it can withstand with high current density and yet with very good activities, meaning to say that it only require low O potential to achieve high current density, for example, like 1 ampere per cm square. And to elucidate the improved electrocatalytic activity by computational method. So this is my research methodology. So during my PhD, I will make the material, I will synthesize the material, and I characterize the structures and see whether the structures can give the desired properties or not. If the properties is not very good, then I will go back to modulate the structures, to change the structures by manipulating the synthesis, the experimental condition for the synthesis. So mostly I will use CVD process or hydrothermal process to prepare my sample. Later I will show you some of my sample here. And after that, sometimes we will fabricate the material with hydrothermal process first, followed by CVD process for further treatment to change the properties of the material. Then after that, we will characterize the sample using physical characterization method, for example, SEM-TEM, to see the morphology features, XRD, HRTM to see the crystal structures, and some of these to see this elemental composition, chemical state, and chemical bonding. After this physical characterization, we will do electrochemical characterization. I think you guys are very familiar with this HER polarization curve, Tafel slope, Nyquist plot, Bob plot cyclic voltammetrics, Faradic efficiency, turnover frequency to find out the intrinsic activity of the HER catalyst. And also we will test the stability of the material by running repetitive LSV or to hold the current, and then we see whether the potential will change or not over time. So we try to build a relationship between the structures and also the performance. So it's a structures properties relation, try to correlate the relationship. After that, we will seek our collaborator to do some computational methods to carry out some insights. For example, we will measure the hydrogen absorption energy. Usually the delta is the delta G. If the closer to 0, the better. And then the formation energy and electronic conductivity. For the formation energy is we try to see whether or not the material can be effectively doped in the material or not. If the formation energy is negative, then we need to say that this dopant can be effectively, is favorable, thermodynamically is favorable to be doped in the material. If it's positive, then you have to be very careful because it could be two phases rather than it begin doped in, it could form another catalyst. You can have two phases, it precipitate out from a matrix. And then we also want to see whether or not the dopant can increase the electronic conductivity of our catalyst. So basically, this is the framework of my work during PhD. All right, so chapter 3 and chapter 4, these two actually are a very similar process, except the precursor I use, one is MOS2, the other is for the WS2. So I'm going to talk about chapter 4 only because chapter 3 is also similar with chapter 4, except the precursor we use are different. So this is why I say transferable, because this method can be used for the other catalysts. It also can be used for MOS2. It also can be used for WS2. So in this project, I try to fabricate nickel phosphide electrode, and after that, I soak this electrode into the catalyst precursor, and then anneal it at 500 degrees C. And then I get my hybridized electrocatalyst. Then this hybrid electrocatalyst perform better than WS2 and also nickel phosphide electrode itself, the standalone electrode itself. So this is the experiment setup. So how do I fabricate? How do I develop the nickel phosphide framework? So I apply rate phosphorus and with a nickel form. And this is 95% of argon gas with 5% of hydrogen. And then after that, the rate phosphorus can react with the nickel form at about 500 degrees C. So I find that at low temperature, for example, like 200 degrees C, the rate phosphorus doesn't evaporate much. However, at around 500, I see that the nickel forms can interact with the rate phosphorus and the nickel phosphide are formed. So these are the sheet structures of the nickel phosphide. At around 800 degrees, I find that these sheet structures will melt and they will like merge with each other. So the surface area is reduced. And that's why I keep at around 500 degrees C. So the features of this nickel phosphide is that it is three-dimensional. Some people, they like to do two-dimensional electrodes. I find that the surface area is limited and the active site could be limited. Therefore, I prefer to use nickel form. And it's macroporous. Macroporous means the electrolytes can go in and out very easily because these are porous structures. So the ions, it can be refreshed, the electrolyte can be refreshed quickly. It has high electrical conductivity for nickel phosphide, and it has high catalytic activity. And also, more importantly, nickel phosphide are both stable in acid and alkaline. So we can apply this material we don't need to consider the chemical stability. Because if you apply nickel sulfide is not stable in acid, so it can easily, it will be like corroded immediately if you put in acid, even without starting the experiment. So we need to find a material that can be stable in the electrolyte we want to test. So basically, this is the step how I perform the experiment. This is a 3D nickel form, pristine 3D nickel form. And then I phosphorize it at 500 degrees C, and then I treat it with WS2 precursor. I soak the template into the solution, and then I anneal it at 500 degrees C for 1 hour. So this is the catalyst I got. So before the annealing process, before the WS2 begin anneal, so we have the 3D structures, and this is the vertical standing nickel phosphide. And after the annealing process, the morphology changed a lot, but surprisingly, we find that the surface area increased. Okay, so this is the structures of the nickel, the WS2 and nickel phosphide hybridized electrode. You can see the sulfur, phosphorus, nickel, and tungsten, they distributed quite uniformly. And under TM, we can see that there's WS2 layer, 9 layer, 6 layer. So they are close to the H, so the H are still very active for the HER reaction. And then we perform Raman spectroscopy to see whether or not the WS2 really grown on the sample. So we grow WS2 on a carbon fiber paper. And then after that, we try to locate the peak. And we see the peak shifted a little bit. So we believe that this is because WS2 is, after the thermal hybridization, it could be intermixed with the nickel phosphide. There's a very intimate electrical and also mechanical integration between both of them. And we find that we also try to find if there's any other product formed during this process. However, we could not detect other bonds in this Raman shift. So this is the XPS results, and we find that tungsten and sulfur doesn't change a lot, and we find that is the phosphorus. The phosphorus is the thing that changed the peak of the phosphorus shift a lot. However, the tungsten and the sulfur peak are very close to the binding energy of the tungsten sulfide grow on the carbon fiber paper. So it means that the electronic environment of the phosphorus is changed in this thermal hybridization process. So, and then the W and S, they don't play very significant role here, perhaps from a perspective of XPS. Then we carry out the HER performance, the electrochemical characterization. So we also have one control sample. For example, we have the WS2 precursor loaded on the nickel phosphide without doing any thermal treatment. So I denote it as WSY because I'm not sure about this stoichiometric ratio. And we find that the black color is platinum rod, and the blue color is our hybrid sample. It is better than the nickel phosphide, and is also better than nickel form, and also the sample that is not begin treated. So this one is our sample, hybrid sample, is better than the other two control sample. And we also find that the Teffer slope is lower compared to others. The lower the Teffer slope is better for the catalyst reaction. And also we have a smaller charge transfer resistance from a Nyquist plot. And we also test the stability over 24 hours in both chronopotentiometrics method and also the LSV method. And then we measure the surface area, and we find that the surface area of the catalyst indeed increased. And we also measure the turnover frequency, the intrinsic activity of our hybrid sample indeed increased. So we try to do some computational study, and we find that this one is the nickel doped tungsten disulfide, and this one is phosphorus and nickel co-doped tungsten disulfide. However, the formation energy of this is very large. It's a positive value. We don't believe that nickel is successfully doped into WS2. So these two results are not very useful for us. We just do a case study. We get a negative value for phosphorus doped WS2. So we believe that the phosphorus has activated the basal plan of the WS2. So these are the case study for the simulation. So I'm going to skip this. All right. So now we go to chapter 5. Chapter 5 is I try to grow two material in a CVD process at one step. So I grow molybdenum disulfide and VS2 in a one single CVD step process. So it's also hybridized electrocatalyst, but I just do it in a single step process. Okay, so this is how I did. I basically try to exploit the evaporation temperature of our precursor. So sulfur will react with hydrogen at about 180 degrees. And this is vanadium chloride. Vanadium chloride will evaporate at around 300 degrees C. And then molybdenum oxide, the evaporation temperature will be higher, 750 degrees C. So if I put the precursor here, what will react first is the vanadium chloride will react with the sulfur first. Then it will form vanadium disulfide. So these are vanadium disulfide. So I ramp up my CVD process very slowly. So after that, I ramp up to about 800 degrees. So you can see that at around 750 degrees, the molybdenum oxide start to decompose and evaporate. So you can see there's a MOS2 grow on the vanadium disulfide. So the thing is that the vanadium disulfide is sensitive to the moistures and is also conductive. So it's good to keep the VS2 underneath the MOS2. MOS2 is not so moisture sensitive, so it can like protect the VS2. And MOS2 is not so conductive. VS2 is more electrical conductive. So you can say VS2 and MOS2, I want to see whether their performance can be improved. That's why I designed the experiment and try to look for some interesting phenomenon. All right, so this is the structures of MOS2 and then VS2. So the VS2 is underneath, you cannot see it. It's fully covered by the MOS2. So this is the MOS2 structures, and I find that under SEM, this is about 20 nanometer in the thickness. And then we do EDX testing. We have vanadium, molybdenum, and sulfur. So when I mix these three figures together, I find that the vanadium, which is the red color one, uniformly distributed over the MOS2. And then we perform the MOS2 microflower. Then we slowly scratch the catalyst from an electrode, and then we do TM. And then this is the MOS2 structures. And we perform TM at a nano level, and we see that vanadium also dispersed uniformly over the microflower of MOS2. So we believe that this is due to the solid diffusion. So the vanadium disulfide we get is vanadium rich, is V1.1S2. So the vanadium is very rich. Vanadium is not VS2, it's V1.1S2. The vanadium can diffuse into the MOS2 structures slowly, and then eventually it will dope the MOS2. Because when we look into the product, the byproduct here, we find that some of the byproduct they should not have extra vanadium source to dope into MOS2. The vanadium source should have already depleted. So we believe is the doping process is gone through the solid diffusion from the underneath VS2 into the MOS2. So this is a very interesting doping process. It's a solid diffusion process. And then we perform the XRD and we find that there's MOS2 and VS2 structures. And we also perform the Raman, that there is no VS2 Raman signal from a sample because the VS2 is underneath, so it cannot be detected. And we find that there's a peak shift in our sample as compared to the pristine MOS2 grown on the carbon fiber paper. So this peak shift, it means that the doping effect is doing something behind, so we can change the chemistry of the electrodes of the MOS2. And this is the XPS result. We're trying to quantify the doping level of MOS2. So we find that the doping level of MOS2 is about 1.02%. So there's about 1.02% of vanadium doped into MOS2 characterized by XPS. So XPS is more surface sensitive. So I believe this result will be more important for electrocatalyst, because electrocatalyst also is also a interface behavior. And then I perform the electrochemical reactions. As you can see over here that this red color is our hybridized sample. It is better than vanadium disulfide and is better than MOS2 itself, standalone itself. The hybridized sample have a better improved performance. And also the hybridized sample, it has a low, this one is somewhere in between of the MOS2 and vanadium disulfide. So I believe the sample is still, it's like the lower the value, the better. But in this case, it's 95. It's somewhere in between the MOS2 and VS2 is. Yeah, it's somewhere in between of them. And then we also perform the Nyquist plot. So this is the MOS2 and VS2 electrode. So you can see it form a semicircle. So if you increase the O potential larger, and then this one, it can form a circle. This one can also form a circle, but the semicircle will be large with a diameter larger than the MOS2 and VS2 significantly. And then we also perform a stability test. So this is a stability test. You can see that there is negligible potential change over 12 hours. And we measure the surface area, and we find that the surface area of our electrode material indeed increase. And also the turnover frequency of our hybrid samples is higher than the standalone sample. And then we also do DFT simulation. So the DFT simulation, we try to do some case study. Here, this color, the blue color is vanadium. So hydrogen is near the vanadium. So this one is hydrogen near the vanadium. Or this is the vanadium, hydrogen is further away from the vanadium. So it's a F words here, further away from vanadium. In both of these case, right, the hydrogen absorption energy are reduced. So as compared to MOS2, pristine MOS2, the hydrogen absorption energy is reduced, meaning to say the intrinsic activity is improved theoretically via DFT simulation after we dope in the vanadium atoms. And then we also perform, we also do some band gaps testing, band gap simulation, and we find that after there's the energy state, there's a DOS above the Fermi level. So it means that conductivity of the material is improved. All right, so this is my last work. This work is focused on in situ derivations of highly active nickel sulfide and molybdenum disulfide nanostructures on nickel molybdenum microcuboid view surface control sulfurization. So this work is dedicated to high current density. So in the first step, I also use nickel form and I do hydrothermal synthesis and I grow nickel molybdenum oxide. This is a microcuboid, 1D structures microcuboid. And then after that, I perform control surface sulfurization. And most of people, they will just perform sulfurization at like high temperature and long time. But in this case, I perform control surface sulfurization. I try to explore the extra room. If you don't perform complete sulfurization, what will happen to the material? And this is very interesting project. So if you recall that if we have a silicon, if the silicon is not pure, meaning to say there are some impurity inside, then there could have some conductivity. So if you don't have a well-crystalline material, well-crystalline silicon, you can play with the properties of a silicon, right? With the impurities, then you have extra hole or you can have extra electrons, and this you can control the material property of silicon. So with that in mind, I also try to control the structures of a material. I don't want to do full sulfurization. I perform at lower temperature and a shorter time. So the control surface sulfurization can introduce some defects, and it also can introduce some new chemical state. These are not very explored by many people. This is relatively new fields. And this is what we have. So first of all, I like to talk about the nickel molybdenum oxide. This is the first step. I grow nickel molybdenum oxide on the nickel form, which is here. So nickel molybdenum oxide we have a nickel oxide octahedron and molybdenum oxide tetrahedron. This is the structures. So if you know crystal field theory, then you know that nickel sites are more active. And then if we perform control surface sulfurization, so this is a nickel molybdenum oxide. The nickel and molybdenums will outward diffuse, and eventually you can react with the sulfur disulfide, hydrogen disulfide, sulfur sulfide, then it can form nickel sulfide and molybdenum sulfide. So these structures is not fully crystalline structure. structures. So if you control the time and you control the temperature, you can change the surface chemistry of this material. So in this case, we have a dual hierarchy structures. So we have a 1D microcuboid, nickel molybdenum oxide, and then we have our active, this is a catalyst, right? We have nickel sulfide and molybdenum sulfide grown on the catalyst surface. Because at high temperature and in the H2S environment is a reductive environment, so the material will reduce. This is an oxide material, so it will reduce. Nickel and molybdenum, they will reduce to form metals. So as it diffuse outwards, it will interact with H2S and it will form nickel sulfide and molybdenum disulfide. So these two materials are active for HER. Now, if you perform full surface sulfurization, you can do it at 400 degrees C for 60 minutes, and then you will fully form nickel sulfide and molybdenum sulfide. Nickel molybdenum oxide, in this case, will fully converted into nickel sulfide and molybdenum sulfide. However, if you perform controlled surface sulfurization, the microcuboid nickel molybdenum oxide still serve as the support, the backstone. So it's the conductive material. This material is conductive. However, for MOS2, this is not conductive. So we want to have a conductive skeleton and then support our catalyst. So this is very important. This is one of the reasons why it can be performed at high current density, because the catalyst we have right now is not by using a spray gun. You spray your material on the carbon fiber paper. At high current density, you can detach, the sample will detach. In this case, these materials are grown directly on the carbon fiber, are grown directly on the nickel form. And then these materials are not like you try to spray or try to deposit the material on top of this material. You grow up. This material grow from itself. So it has a very intimate, connection. So it will not detach easily. And that's the reason why it can perform at high current density. All right. So this is a TM structures. You can see that this nickel molybdenum oxide and the surface are nickel sulfide and molybdenum disulfide. These are very highly porous structures. And we can detect MOS2 and nickel sulfide in the EDX and also the HRTEM. So this highly porous structure is very advantageous for HER reaction because these are extra room, that they are more active sites for the HER. So we find that if the TM taken at close to the center of the crystal and close to the edge of the crystal, the crystallinity is different. So close to the center, we have more crystalline structures, and close to the edge, we have less crystalline structures. You can see that these diffraction spots are more diffuse. So this is good for us because this result actually can it's aligned with this result. You can see this is mesoporous. It's less crystalline, and they are active site for HER reaction. And more importantly, we do STEM, and we find that during the controlled surface sulfurization, there are new phase form. This is 1T prime MOS2. If you perform full sulfurization, you can only get MOS2 and nickel sulfide. And then if you perform controlled surface sulfurization, in addition to that two compound, you have one compound form, 1T prime MOS2. So this compound can only form like at the intermediate phase. At high temperature, this compound will be converted to 2H-MOS2. And these materials are very conductive, and it also very active for HER reaction. So this is very important slide. So we perform the XPS, and we see that as we control the temperature and we control the time, 0 minute, 5 minute, 10 minute, 15 minute, and 60 minutes, you can see the shift of the nickel peak, and you can see the shift of molybdenum peak, and you can also see the shift of the sulfur peak as well. So if you know how to do XPS fitting, then according to the literature, you can identify different types of the terminal for sulfur. Terminals, unsaturated sulfur or bridging apical sulfur. Then by controlling the temperature, by controlling the time, then you can control the species of this active sites. So if you can find out which active site is more active, then you try to increase the number of active sites by controlling the time of sulfurization. So this is something missing. This is a piece. This is a missing piece in the full sulfurization that people don't aware of. This transient state can really bring some interesting phenomenon. All right, so we'll perform hydrogen evolution reaction, and this is one of my best work in terms of the performance, because I can get about 1,000 MA per cm square is 1 ampere. 1 ampere is very high. It's a high current density performance. So, however, if you look at this one, platinum and carbon in this case, it will stop here because at high current density, about 150, it will start to detach already. So the curve will be very, very ugly. So it is not meant for testing at high current density. However, our sample CSS, control surface sulfurization, nickel sulfide and molybdenum sulfide, it has very good performance at high current density. As compared to this full sulfurized nickel sulfur and molybdenum sulfur, the performance is very mediocre. And we also perform the we find out the Tafel slope here, and we perform the Nyquist plot. Everything I think is quite you guys are very familiar with. And we also perform a stability test over 50 hours, and you can see that after 50 hours, the current can go back to here. And after that, we also try to find out the surface area of the material, and we find that the control surface sulfurized catalyst indeed has a higher surface area, higher electrochemical surface area compared to the full sulfurized nickel sulfur and molybdenum disulfide. And it also has a better turnover frequency as compared to the fully sulfurized sample. So what I want to emphasize here is the control surface sulfurized is a very new method. There's extra room for you to explore, not only in the hydrogen evolution reaction, maybe in the ORR, oxygen reduction reaction, or oxidation reactions, or carbon dioxide reaction. It could also be useful. And then, okay, this is almost come to the end. So I like to summarize what I did. So I find that the synergistic effect arises from doping effect. The doping effect can increase the number of active sites. It can also increase the intrinsic activity of the sample. It also increase the electrical conductivity. And then we have a one-spot CVD process. We can hybridize two catalysts together at one step using different temperature, the precursor temperature, growth temperature. And then last but not least, we use controlled surface sulfurization, and we apply the bimetallic oxides to get a high current density electrode. So these structures are dual hierarchy structures. They have high activity, they have high stability. So I pinpoint my material performance in this table. So all the other values are from the literatures. And then we tried, this is the future outlook. So just now I discussed, I use nickel form and convert into the nickel phosphide. Can we use can we convert nickel form into nickel selenide, nickel nitride, and so on? Or can we apply the same idea for iron form and then convert the iron form into iron phosphide, iron selenide, and iron nitride? Can this catalyst be useful or not? So this one don't know, need to try. And we also can try different novel material. Just now I tried VS2. Can we try VSE2, vanadium selenide, or rhenium selenide, titanium disulfide? These material are not explored yet. And I also mentioned the bimetallic oxide AbO4. So can we try to, if we are doing the carbon reduction reaction, CO2 reduction, can we try to put copper inside and maybe group 1 or group 2 element inside? Because group 1 or group 2 elements, they are not very good for water reduction. So if you want to improve the efficiency of the carbon reduction reactions, so could we put some group 1 or group 2 material so that it can inhibit water splitting while we have a copper here, and then maybe we can have a very good result. So all these could be applied for my current project as well. And So in order to understand the mechanism of HER, so that's one of the reasons I joined. When I do my first postdoc, I join a group that has a SDM, and I learn how to do calibrations of the stem. Okay, I think that's all for the sharing.
Okay, thank you, Shuhan, for the very interesting presentation about hydrogen evolution. I think you covered the topic really, really quite well. And I think we have two questions in the chat. I think the first one relates to your first work. Was the amount of tungsten sulfide growth controlled? And how much tungsten sulfide I think was optimal for hydrogen evolution?
Oh, okay. Yes, thank you. The amount of of tungsten disulfide was controlled. It's not shown here. It's shown in the supplementary document. So we try to like sort the nickel phosphide and then dry in the oven, dry oven, and then we sort it another time to increase the loading. And then we try a few samples, like 4 to 5, and we find out there's one optimal loading for the tungsten disulfide. Because if you always load, if you increase the loading, right, then the conductivity of the tungsten disulfide will be reduced. So it's not like you have more loading of tungsten disulfide is better. No, the conductivity will be compensated as well. Other than that, the dispersion of the tungsten disulfide may not get very well if you increase the loading. So that would be an optimal loading for the tungsten disulfide.
Okay, thanks, Shuha. And the next question is, are the nanostructures of your catalyst stable and maintained after using for long periods of hydrogen evolution?
Okay, thank you. I think the structures of, I think I'm not quite sure whether this question refer to which structures, but generally speaking, all the material that is able to publish in the paper, they actually require, they will see the SEM or TM structures of the material after the testing of the hydrogen evolution reaction. I can tell, what I can tell is that the morphology will change slightly, but the performance doesn't drop. And most of the times, right, the morphology will be a bit ugly and the material will be oxidized or reduced because it is in a corrosive environment. Some material will be reduced and some material will be oxidized. For example, if you have a nickel phosphide, then the phosphide, you can see that the phosphide is in the XPS result, you can see that the phosphide, it forms like a phosphate because in a very corrosive environment. And sometimes the material will be reduced. The structures generally will change slightly. However, the performance will not be compensated so much. I think I have one slide. Let me see whether I have a slide here. Yeah, these are the structures. So after the 22 hours of testing, it becomes a bit ugly. Yeah, and then you can see that that the phosphate will form here. Phosphate form is the oxidation reaction. Is the oxidation reactions. Although in the cathode we have hydrogen evolution reaction, it should be a negative. Is a negative potential. In the corrosive environment, everything can happen. So I think that maybe that's all for I answer the question. Did I answer the question? I think.
Yeah, I think they changed a little bit, but the main thing is the performance maintains, right? That's what you're trying to say. And I did catch it like 22 hours, is it? Most of them about 22 hours. Okay, so it's just like relatively kind of stable. Okay, are there more questions? If you feel free to just unmute yourself or write something in the chat. Okay, if there are no questions, maybe I would like to ask a question. You use all these elements like phosphorus, sulfur, tungsten, molybdenum. Why do you, I think you didn't really cover this, like why do you decide to use all these elements? Like what was the strategy that you try?
At first we think of is earth abundant and we have some senior doing this catalyst. So the chemical is in the lab. So we are ready to try this chemical. Yeah.
Okay, so you just happen to have these like chemicals in the lab, and then you try them.
And yeah, we have senior doing very similar work, and then I'm reading the MOS2. At that time, it was very hot topic, and that's where I tried to do MOS2 for hybridized catalyst.
Okay, okay. And also the literature, there was people working on it, so that you decided it was interesting.
Yeah, it's a good starting point because there are some result there, and then we know because Jaramillo is a very famous in doing HER. So at that time, it's very hot topic. So he discovered MOS2 and also identified the active sites. So I think that's a good starting point to work on the hydrogen evolution reaction using the material. Yeah.
Yeah, yeah. I think you also shared some computational studies, right, on your material.
Computational study.
Yeah, yeah, like a DFT simulation.
Yeah, correct. Computational study. Yeah.
Yeah, yeah. So you were able to shift the hydrogen binding energy of nickel through all these kind of doping and growing of heterojunctions. Is that correct?
Yeah, correct.
Okay, okay. But I think from what I see is that the composite structures are a bit disordered. Sometimes there's a big interface, and then essentially the interfaces are not very homogeneous.
Hmm.
What do you think is the main active site? Is it the interface point, or is it the nickel itself, or is it the additions on top there as the main active site? Like what do you think is the main active
Okay.
site of these composite materials?
For my understanding is the interface is not very clear in the study and also in the TM. I couldn't identify the interface. So it's more likely like the PFT performance is like trying to find a trend. So we have the MOS2 structures or WH2 structures. Then we try to remove the atoms we remove the sulfur, and then we put in the phosphorus, and we want to see whether the hydrogen, the Gibbs free energy of hydrogen before and after absorption will be reduced or not. And then we find that after we introduce the phosphorus, the Gibbs free energy can reduce. So we believe that the basal plan, which is originally inactive, is activated so that increase the number of active sites.
Okay, okay. So basically, it's the edge sites are active, but the basal sites are not active. But then with your doping or your
Yes,
addition of heterojunction, you also activate the basal sites.
yes, correct.
Okay, okay. That's interesting.
I would say like most of my work is more like engineering, because in material science and then in my times, right, the simulation is not very hot. Like no one in our department doing simulation, and in undergrad or PhD we also don't learn a lot of simulation things. So our simulation is like we are seeking collaborator in other universities. So we only like grow material and do physical characterization and electrochemical characterization. That's what we can do. We don't have much science behind. We have like more on the engineering.
Okay, okay. Understood, understood. Okay, is there anyone else have questions for tonight? Okay, if not, maybe let's thank Dr. Yu Shuhen for this very wonderful presentation today. I think he did a lot of very interesting work on the material science side. And then hopefully he can continue to build on this, and we have a lot of very interesting work together. Okay, thanks everyone. This is the last class for the module, and then there'll be I think the next event that is coming up is I think homework is due on Monday morning at 9. We have a Good Friday long weekend to complete your homework, and yeah, just feel free to send emails to me or the teaching assistant. He will be able to help you with answering any questions. Okay, if there's nothing else, and then there'll be the exam on the 6th of May. Yeah, so that will be about a 2-hour exam with about I believe there'll be 8 questions. Okay, so if there's nothing else, I hope everyone has a good night. Hope you enjoyed the 3 guest lectures that we had today. Okay, have a good night and enjoy the rest of your evening. Bye bye.